So today we'll be continuing from chapter properties of solids, and we'll be continuing from the portion from where we left off during the live class. We finished Poisson's ratio, right? So from there we are going to start the next topic from the same chapter. I hope you remember what is Poisson's ratio. Poisson's ratio says it is the ratio of lateral strain by longitudinal strain, right? I hope you remember this section, right? So from here we are going to the next topic of the same chapter, and this derivation again is usually asked, right? And this is the only question other than stress is proportional to strain and the corresponding terms which you have learned regarding bulk modulus, etc. So this topic or this equation or this derivation is only derivation present in this entire chapter, that is deriving elastic potential energy. Elastic potential energy, right? That is when a wire is under stress, right? So that means you are going to do some work, right? Suppose this is a wire piece. I have pulled it outside, means I have done a force so that there exists an extension of this rod or this piece, right? So then will be a displacement, or that elongation is just like a displacement. So that means I am doing some work, right? So this work will be stored inside this equipment or this solid as what is known as elastic potential energy. So that is a work which you are doing to bring it to a new position, right? That work will be stored in this object as a potential energy. So if you remove that force, the object comes back to its initial form. That means the potential energy again is lost back, right? Clear? So this much you understand. So we are going to derive an expression for elastic potential energy. So it will be in terms of both stress and strain. Clear? Suppose for this I am going to take a wire which is having length L. Let's say it is having area A, right? And it is subjected with a force F, so that the wire is undergoing an elongation of X, right? The length is increased by a little bit by X meter, right? So what is a Young's modulus? It is lateral stress by lateral strain, or longitudinal stress by longitudinal strain, right? So it is, it's lateral, it is longitudinal stress by longitudinal strain, right? So in place of delta L, here the elongation is X, so I will write it as X by L, right? Clear? Right. So this much section I hope you have understood. So I'm just going to rearrange this guy so that from this equation I can write F is equal to AYX by L, right? I require this term later on, right? So suppose further I can say if the elongation happened, right, is only dl, not the x but dl. That is, if I do a small work dw, right, it is due to the application of force F into, and the elongation is only a little bit dx, or in place here I will write dl. I'm repeating again. Suppose I applied a work, or I can say applied a force F to bring about a length change of dl. That means I will be doing a work dw. So I can write dw is equal to F dot dl. Can't I write it so? Yes. Here let us say I am going to change into dl. In place of that I am going to write dx, because here I have written x, right? So I will say dw is equal to F into dx, but dx is a small change in the length and the corresponding work is dw. In place of F I am going to replace it with this previous equation so that it becomes AYX by L dx, right? Clear? Now that means this is a small work which is now done for an elongation of small distance dx. This much clear? Right. That means if I'm going to change for or going to calculate total work for bringing a bigger change of delta L, right? Right, that's why you write Young's modulus is for what? F by A divided by delta L by L, right? So here I'm going to say that the change in length which I'm going to bring about is delta L. So the total work which I will say is from bringing the length change from 0 to delta L dw. I have to integrate this dw. Sorry, let me make my phone silent. Okay, so in place of dw I can write 0 to delta L. Here I am going to replace it with this equation a y means Young's modulus x by L dx, right? Now from here you can write some constant terms, bring it outside. It is a y by L, right? 0 to delta L x dx, right? Now what is integral x ds? It is x squared by 2. Sorry, here I am supposed to write ay, right? Ay by L squared, x squared by 2, right? Upper limit delta L, lower limit 0. Aha, sorry, I thought I made it silent. Right, so that means here in place of x squared, now I have to substitute it with delta L, right? Ay by L delta L squared by 2, right? Now I'm going to bring some terms commonly at one side. Yeah, why it is so? Okay, that is equal to, right, half into, right, y into delta L by L, right? This delta L is having square into a. I have just rearranged the above equation, right? Now what I am going to do is half into y into delta L by L into L. I have bring an extra L over here, then I am going to multiply a L over here, right? So this denominator section becomes what? L, and there is a square now, so I can write it as delta L by L whole square. That is 1 into Young's modulus into delta L by L is strain square, area into length is volume. Right, now Young's modulus is stress by strain, right? So I can write stress by strain into strain squared into volume, right? Or I can write it as half into stress into strain into volume is work, right? So this is the equation for work, right? And this work is stored as potential energy while doing, or stored as potential energy in an object, right, when it is undergoing elongation. Right, someone asks you what is work done per unit volume, then it is half stress into strain, right? So usually this is what is stored as our energy. Work done per unit volume is something which is usually stored as energy, right? So you can even say half sigma into epsilon, right? Clear? That is potential energy which is stored. Clear? Amount of work was stored per unit volume, that is, or work done per unit volume is usually what is stored as a potential energy inside that object. Clear? So this is expression for it. Yeah. Now there is another section, or I would say the last portion of your chapter, which is application of elastic behavior of materials. This part is something which is usually asked other than the stress strain curve as 5 mark question. Okay, so let's move on to that one. First application which you have to learn or in your syllabus itself the given is first is to select the rope, that is why the rope which you use in the crane, right? The cranes are used for loading or to get hold of heavy objects, right? So the rope you might be seen that it is made up of steel, right? And they are twisted means it is just like braided. Lot of ropes which are made up of steel are braided together to make a single section. It is not a single rod or steel, it is a rope made up of steel, right? Why that rope is such that if you can definitely make a steel, right, steel rod, yet it is not a steel rod but a rope made up of multiple wires of steel. That is what is used in a crane. Why it is so, that is what we are going to deal with the help of studying elastic property section. We can say why you are using a twisted or a braided rope section in the crane, right? That is, you know, this for the steel, it is a material, right? The steel is having a yield strength of how much, around 3 into 10 to power 8 Newton per meter square. That means it can tolerate this much amount of stress only. More than this stress it will become, or will become so much, no, that is, I hope you remember, it is a point after which no reason of the material to come back to its original position, right? So this is the limit of stress which can be tolerated by a steel section, right? Suppose you have to take a load, let's say a load of 10 to power 4 kilogram. This much amount of load you want to take by using a crane, right? So obviously a rope is required. So that means the rope which is made up of steel, which has only this much of yield strength, and you are using it to carry this much weight. That means you can use stress is equal to what, force per unit area or load by area. Load is this much mg, right? So this much mg in this is the mass, and g will be another 10, right, divided by area is pi r squared, right? Pi is 22 by 7, right? So you can replace stress value as 3 into 10 to power 8. You can calculate radius. You will find the radius as around 1.03 centimeter. That is this much radius wire or steel you have to use for taking this load of this much weight. See guys, 1.03 centimeter is very small, no? Right? So even if you are making a rod of 1.03 centimeter, that much length means any point it can break. So in order to avoid this problem, what you are doing is you are having multiple steel section, multiple wires you are twisting so that this multiple wires entirely make a system just looking like a rod, and that rod will be having a radius of 1.036 centimeter. Clear, right? So this is the application of learning elastic or behavior of elasticity we have learned, right? Now the second application is, see, while constructing a bridge, the other example which you can talk about is bridge, right? So while constructing a bridge, a load of traffic will be there, that you have to check how much can the bridge can tolerate. There will be a lot of vehicles on that bridge, right? So how much vehicles it can withstand, right? That should be calculated beforehand before making the bridge, right? Yeah, that is it has to be kept in mind that the extension how the ropes etc. You would have seen in the bridge construction there will be rope system, there will be pillar system, right? So the entire thing has to be calculated, right? So to study the elastic behavior of the materials, let us consider that there is a beam of length, right? Let's say this is there is a beam section of bridge, right? And let's say it is having length L, right? and let's say breadth is b, right, and the depth is d. The breadth means, if I draw like this is a beam, so this is the breadth, right, this is the breadth and this is depth. Clear? Right? So a weight, suppose you can calculate this. Suppose a weight is hanging over here like this, right? Let's say that weight is w. Then you can understand that then by this weight section this will bend like this, right? I hope you understood what I meant. That is, after the weight is coming like this, then the beam will be bending like this. The proper diagram is there in your textbook. Okay, clear? This much is clear. So let's say initially the beam was located or straight, right? It bended means, let's say this angle is delta, right? That is this much dipping is there. And it is calculated that delta is equal to W, that is a weight which is hanging, into L cube, that is length, divided by 4b d cube y. It is something which has been experimentally found, that this how much sagging, right? This delta is called sagging, right? How much sagging the beam is having is equal to or proportional to how much weight is hanging here into how much cube of the length of this beam divided by 4b d cube. D cube is the depth, b is the breadth, and y is the Young's modulus. So if you want to reduce the sagging of the bridge is not welcome, right? So in order to reduce the sagging, what should be increased? You cannot touch the width, or you cannot change the weight, because the weight is something which exists, right? The amount of vehicles will be there, a limit can be placed how much cars can travel through it, right? But actually that a bridge cannot be given a maximum condition, that only this concrete bridge can only tolerate 1,000 ton, etc., right? There is a limit. So you can say a limit of weight that can be tolerated by it. Length is something which you cannot touch, because you usually construct a bridge from one end to another, so the length is there. So obviously you can touch breadth and depth, right? That also, but cannot be compromised much. Why? Breadth and depth also determines whether it will break or not, right? So the thing which you can alter is Young's modulus. That is, when Young's modulus is less, delta will be greater, right? Inversely proportional. When Young's modulus is greater, delta will be lesser. So in order to have less sagging, it is better to use the material, right? The material which is used to construct this beam can be having a Young's modulus which is very high, right? So in order to make a bridge which doesn't sag due to extra weight, you have to construct that bridge using a material which is having higher Young's modulus. Clear? Right? Similarly, you can even talk about the while constructing the bridge, you will have seen this is the beam. There will be what is called as supports, right? Right. These supports usually are shaped I. If you see, they are always shaped in the I shaped. I shape means like this. Why it is so? See, if it had been a straight bar, that is, this construction, this type of extension is not given, you're just having straight type of connections, then after the end, suppose this entire section is having, this is the bridge, right? You are having a lot of cars over here, right? So that means a lot of weight on a small area. So later on this will bend and it will undergo breaking, right? So what you are doing is you are increasing the area, right? So that the weight will be distributed throughout this area, right? So the entire force or entire pressure doesn't come to this length. Clear? So maximum area support is given. That's why you are making bridges are made like this. Clear? So this is the application of no elastic behavior of materials. I hope this much is clear, right? So by this we are completing the theory section of this chapter. So I want to talk about little bit problems, which is very less. So let me look into that problem section, and in this video itself we'll start the next chapter also. So I want to make sure that you understand actually as per NEET or any entrance chapter, the two chapters, that is the mechanical properties of solids and the next chapter mechanical properties of fluids, are actually a part of same unit itself, right? That is, I believe, the chapter 10 and 11, right? That is your chapter 10 and 11, right? Right, this chapter 10 and 11, or it is 9 or 10, I don't remember, right? So properties of matter or properties of solid, right? Mechanical properties of solids as well as mechanical properties of liquid are actually a part of a single chapter called properties of matter as per NEET, right? So once I finish solid section, I will straight away jump to the liquid section. Clear? Right. So before going to the solid section, let's do the some numerical problems. Let's move on to the first numerical section. One end of the uniform rod of mass 1 kilogram and area of cross section 2 into 10 to the power minus 4 meters squared is suspended from a rigid support, and an equal mass of 1 kilogram is suspended from other end. The stress at the midpoint of the rod. That means you are having a rigid support and there is a rod like this, right? And at this end of the rod another weight is kept, which is of 1 kilogram. This rod is also 1 kilogram, right? Sorry, how much is the kilogram? The rod is 1 kilogram. Its area's cross section is 2 into 10 to the power minus 6, right? 2 into 10 to the power minus 4 meters squared, right? So you are at what is the this midpoint, how much is the stress, right? This is a question. So you know that the acceleration due to gravity, or the weight, which we'll talk about weight, total weight which is acting on this midpoint will be 1 kilogram, this one, and only half the kilogram, right? Because here the weight is acting only for, you're asked for calculating the from the midpoint, means you are only calculating the weight section of the half section of the rod, right? So the total weight which is acting at the midpoint section will be 1, which is this guy, plus half the kilogram of this much section. So half into g, that is, this is 3 by 2g, right? So 3 by 2g means 3 by 2 into 10, that is 15 Newton is something, or the weight which is acting at the midpoint. I'm sorry regarding my dog is barking like anything. Don't know what happened to her. Now the question can be easily solved. You are asked what is stress. Stress is equal to force per unit area. So force is this much, right? And how much is the area given? 2 into 10 to the power minus 4. So you can calculate it as 7.5 into 10 to the power 4, right? Newton per meter square, right? So that is the stress. So you have it as option B, right? Let us do to the next question. The breaking stress of a material is 10 to the power 7 Newton per meter square. The density of the material is given as 5 into 10 to the power 3 kilogram per meter cube. What should be the length of the material so that it breaks by its own weight, right? So that means here the stress is due to weight, right? Clear? And you are asked how much is the length change. Clear? Right. So how would you solve this guy? So this is a derivation section, or derivation means I will say this is a new section which I have not taken now, but basics I have taken. Clear? So first we have to have an idea of what a stress is. So I can write stress is equal to weight by area, because here the weight is the hero, right? Read the question again, you will understand. Breaking stress of the material is given, right? So we'll start with stress, and you are given the density of material, what should be the length of the material so that the material, it breaks by its own weight. So the stress is given by what? The object's weight. So the force per unit area I will write now as weight by area. Clear? And the weight is mg by a. Alright. And now mass, now density is given, means I have to write mass in terms of density. Right, and mass is equal to volume into density. Here I will write area into length as volume into density into G divided by A. Now A cancels. I can write stress is equal to L rho G. Right, from here can't I write L is equal to stress by rho G? Yes, and you are given the breaking stress is given as 10 to power 7, density is given 5 into 10 to power 3, and G obviously is 10. After calculation you will get 200 meter. So this much is the length which is possible, so that this material doesn't break down by the stress of its own weight. Clear? Right? So we'll go for the next question. Before that, let me drop this section. So when you are reading the question, you have to understand what answer you require. What is the thing which is asked? Right. Now the next question, third one, the length of wire is x1 when the tension in it is T1, and x2 when the tension is T2. Find the original length of the wire. Right, so the length of the wire is x1 when the tension is T1, that is when tension T1 is there, the wire's length is x1, and when the tension T2 is there, the length is x2. So you're asked what is the new or original length, from where the extension came up. Right, so let us say x is the original length of the wire. So delta x1 will be the new or the initial change in length is now change in length, or now new length minus old length, and the second extension is equal to 2 minus x. Yes, now what is Young's modulus? Young's modulus is force per unit area. Here the case is regarding tension, right? And Young's modulus of a material is always constant irrespective of how much forces you are applying. Young's modulus is a constant for any material. So for the first case, I can write Young's modulus as force per unit area. I will write it as tension by area, right, divided by extension, that is delta x1 by original length is x, right? Or I can write this one as T1 by A into x by delta x1, right? Now similarly, while from the second case, Young's modulus is tension by area divided by delta x2 by x, or I can write tension by area into x by delta x2, right? Now, now from these two expressions, these two are equal, right? LHS is equal, so I can equate these two guys, right? So when I equate these two guys, XX cancels out, AA cancels out. So I can write T1 by delta X1 is equal to T2 by delta X2, right? Now what is delta x1 and delta x2? You have written as x minus x1 or x1 minus x, right? This is x1 minus x is equal to, this is t1, sorry, t1 divided by x1 minus x equal to t2 divided by x2 minus x, right? So from here I can write x is equal to t2 x1 minus t1 x2 divided by t2 minus t1. You can get this value from solving this equation, right? So this section, listen properly, we derive basics things are same, only we are reaching the questions answer by a trickier section. So one thing which is very important, you make it very understandable, is Young's modulus of a material is always constant, right? Only depends upon the type of material which is used. Clear? Sorry about my dog is barking. On to the next question. This one, fourth one. A metal ring of initial radius r is fitted into a wooden disc of radius capital R, that is greater, capital R is greater than small r. If A is the cross sectional area and Y is the Young's modulus of the ring, then the tension in the ring is. Now, this is a question which is not understandable by you guys because it's a concept based question. So you are asked what is a tension, right? So tension means actually it is a form of force. So you, in this chapter, force etc comes in which term? It comes in stress, right? So we'll start with stress. Stress is equal to force per unit area, or I will write here as tension per unit area, or I can write tension is equal to stress into area, right? So area, section etc, it is very easy because area is given as A, you can just write it as A. But the problem is, how can I derive stress, right? Now stress, you can get it by using Young's modulus, right? Young's modulus is equal to stress into strain. So someone asks you what is stress, you can just write Y. No, it's not stress into strain, no, sorry, stress by strain happened to me. Y is equal to stress by strain, right? So I can write stress is equal to Y into strain, right? So I can just write here Y into strain into area. Yeah, but the problem is Y is given, strain is not directly given, so I have to find strain. So strain, right, is change in length by original length, right? So here change in length means, guys, it is a what? Your circle, ring is a circle. So length means here the change in what is happening, change in circumference is happening. So initially the length is 2 pi r. Now inside that you are going to fit another ring of radius r, right? See, a brass and not this one, a metal ring of initial radius r is fitted into a wooden disc of radius capital R, means you want to increase this radius r ring into the wooden disc radius so that it will be approachable, right? Clear? So in, you are having a length change to here, right? Divided by its original length is 2 pi r, right? So I can write here as capital R minus small r by r. This is strain. Now I am going to substitute this value over here so that now tension is equal to Y into strain becomes this term into area, right? This is the expression of tension. So straight away mark this as option C. Alright, now let us move on to the next question, that is fifth one. Brass and steel has Young's modulus this and this respectively. If brass wire and a steel wire of same length are to be extended by equal amount, that is they are going to have same extension under the action of same force, then the radii of wires RB and RS, right? The brass one's radius and steel one's radius ratio, right? So now ratio, right? That. So how would you approach this question? So you are having two materials, means they are having two Young's modulus, right? So Young's modulus is stress by strain, that is force by area by change in length by original length, right? So I can write force by area is, let's say it is pi r squared, right, into L by delta L, right? From this term you are told in this question that F is constant and extended by same length. Initially their length was same and pi is constant, so I can say Young's modulus is inversely proportional to radius squared, right? Or I can write, in this case, let us talk about brass and steel. So steel's radius squared by brass radius squared is equal to Young's modulus of brass by Young's modulus of steel as per this equation. Yes. So I can write Young's modulus of brass is given as 1 into 10 to power 11 and steel it is given as 2 into 10 to power 11. I can write this as 1 by 2, or I can write Rs by Rb is equal to 1 by root 2, or I can write Rb is equal to root 2 Rs, or Rs is equal to Rb by root 2. In any way you can write. Clear? Right? So this is the basic is you have to understand the question. That's the basic thing. Oh, ish. Ah. Let's move to the next question. Two wires having cross-sectional area A and phi A respectively but having same Young's modulus and volume are taken. If the first wire has an elongation delta L on applying a force F, how much force is needed on the second wire by the same amount? To extend, okay, you want to stretch it by same length, so how much force has to be applied? Each is having different cross-sectional area. So delta L, that is, Young's modulus is force per unit area by delta L by L. From here I can write delta L is equal to FL divided by AY, right? So I can now write what happens if I multiply A and A downwards. So it becomes length into area's volume, right? So I can write force into volume divided by A squared into Young's modulus, that is change in length, right? Or I can say that if L is constant and you are said that it is having same volume, you are having the Young's modulus constant, right? So I can say force is directly proportional to area square. F is proportional to area square. So I can write here F2 by F1 is equal to A2 squared by A1 squared, right? And you given second one's area is 5A and initial one's area A, so it will be 25, right? 5 squared is 25. Now that is second one's required force will be F2 is equal to F1 into 25, or it is 25F. So second one requires this much amount of force. Clear? Right? Now let us move on to the next question. So your question is, how much pressure change will occur if volume of 1 liter water changed by 2%, bulk modulus is given as 2.2 gigapascal, right? So how would you do it? So this bulk modulus etc means you are talking about hydraulic section, right? So initial the volume was 1 liter, right? And the change in volume or change is asked as 0.2 percentage, right? This much is given. 0.2 percentage means 0.2 by 100, right? Or I can write it as 2 into 10 to power minus 3, right? So bulk modulus, I hope you remember, it is bulk modulus is equal to force per unit area by change in volume by volume, and there is a negative sign. If you don't require the negative sign also, it's okay. So in place of pressure, force per unit area, here I will write it as pressure. That also I have taught you, right? Or I can write this as this delta V by V here goes like this, PV by delta V, right? I can write it this also, right? Now in place of force per unit area, I can even say it is change in pressure. So I can write here delta P by, or delta P into V divided by delta V, right? So from here delta P can be rearranged to get as B into delta V by V, right? And bulk modulus is 2.2 into 10 to power minus 3, and delta V by 2.0, this what is V is given as this 2.2 into 10 to power 9, right? 2.2 into 10 to power 9, that is bulk modulus, and delta V by V is 2 into 10 to the power minus 3. So you can find the pressure, right? You will get 4.4 megapascal as the answer, right? So you are asked how much is the pressure, you just have to use the bulk modulus equation, right? The compressibility of water is 4 into 10 to the power minus 5 unit pressure, atmospheric pressure. The decrease in volume of 100 centimeter cube of water under pressure of 100 atmosphere will be. So this is a factor which you have to know, which is compressibility. This is not your textbook section, guys. This is a neat term or neat section term. Your bulk modulus inverse, that is 1 by B, is called compressibility. Compressibility is called 1 by B, right? It is represented by C, right? So you know B is equal to P divided, or P into V by delta V, right? So 1 by B or C is equal to delta V by PV, right? Or I can write as PC is equal to delta V by V. Clear? Very easy, right? Now, right, so you are given the compressibility of water is 4 into 10 to the power. Okay, this is something I've given from your side. Write it down. We have not moved to the question till now. You are given the compressibility of water as how much? 4 into 10 to the power minus 5 unit, right? C is given and the decrease in volume is given, right? So you are asked volume is asked. Okay, you are asked delta V. You are given initial volume, that is 100 centimeter cube of water is there, and you giving a P of 100 atmosphere. Then what is the change in volume, right? So you have written down this much equation, I believe so. So C is equal to delta V by PV, right? And from here C is given as 4 into 10 to the power minus 5, that is equal to delta V is supposed to be found. P is 100 atmosphere and initial volume is 100 centimeter cube. So you can find delta V is equal to 0.4 centimeter cube, right? So I wanted to introduce this term. So the next question is also regarding compressibility itself. So this much section I'm not going to rub it off. Next question is also the compressibility of the fluid in spherical form is C. It is subjected by a uniform pressure P, the fractional decrease in radius. That is, you are asked how much is the fractional reduction in radius. This much clear? So this is something which you have to learn from your first chapter. Why? See, from here you can write PC is equal to delta V by V. That is, PC depends upon change in volume, right? Change in volume means volume is directly proportional to R cube, right? So this is just like delta V by V is our absolute error in the case of volume, right? So volume is proportional to R cube means delta V by V will be equal to 3 into delta R by R, right? That is how you have dealt in the first chapter. Power section comes as the numerator. This is the relative error or absolute error section you have learned, right? So this is delta V by V. I can write it as delta 3R by R. So I can write PC here it as 3 delta R by R. Or I can write delta R by R, that is the relative change in the radius, is equal to PC by 3. Right? So this is the answer here, PC by 3. Right? Now 10th question, a cubical block of 50 mm has its upper face displaced by 0.0125 millimeter by a tangential shearing force of 10 kilonewton. The rigidity modulus of the material is being asked, or you are asked shearing modulus, that is G, that is shearing stress by shearing strain, right? And I've told you shearing stress or whatsoever it is force per unit area, and shearing strain I can usually write it as tan theta, and I told you that angle is very small, so I can write it as theta. right? So it is f by a theta, right? This can be written as f by a theta, right? So f is given as 10 to power 4, a is 50 into 10 to power minus 3 square, right? It is a cube, right? So a square, a into theta means tan theta itself, it is what, 0.125, that is x delta x by l, that is 0.125 by 50, right? Clear? In expression, if you want, you can write the theta because you got 0.125 from there itself. Now the calculation is from your side, right? You will get the answer as around 1.6 into 10 to power 9 Newton per meter square. Clear? Right? Right. Now let us move on to the 11th question. See, a material has a Poisson's ratio of 0.5. That's the question, right? 0.5. If the uniform rod of the material suffers a longitudinal strain of this much, what is the increase in its volume? See, this is a straightaway answer I can give you by what? Direct answer, but I will do by the lengthy large process also, right? So first, what has been given, a Poisson's ratio is given, that much clear, and you are told that it is having longitudinal strain, that is it has increased by length, right? This delta L by L is given. What is the percentage change in volume means you are asked what is delta V by V. So what happens is when you are having a longitudinal extension, there will be lateral contraction, that is the diameter decreases, right? When you are increasing the length, the diameter decreases. So longitudinal extension means lateral contraction, right? So the change of that means the volume remains unchanged, right? So the changes in the volume will be cancelling each other. So I will say delta V by V is equal to 0. Right, this is a theoretical section which I am taking, right? So I can even explain it we are using a numerical section. Please keep that in mind. You can straight away answer it without numerical section, right? I hope you understood that also, but I wanted to explain by numerical section also. So volume, I can write it as pi r l or pi r squared l. Let us write this L as capital letter L, right? So delta V by V, right? See, now this error section from chapter 1, delta by V, I can write 2 into delta R by R plus delta L by L, right? So what is Poisson's ratio? Poisson's ratio is change in, right? You can even write minus because the radius is decreasing. So you can write it as minus delta D by D, or I can write it as minus delta because radius and diameter same, divided by delta L by L. That is Poisson's ratio. Poisson's ratio also is sometimes, or no, most of the time it is represented by sigma, that is just like our stress, right? So from here I can write delta R by R is equal to minus sigma delta L by L, right? Now the sigma section is given as minus 0.5, I can write, right? And delta L by L, length change is given as 2 into 10 to power minus 3. So I can write it as minus 10 into 10 to power minus 3, right? Now volume is, or if someone asks you volume section, I just have to substitute from here. Delta V by V is equal to 2 into, okay, here I was supposed to write delta R by R now. 2 into delta R by R means it will be equal to 2 into minus 10 power minus 3, alright, plus delta L is 2 into 10 to power minus 3, right? So there is a minus term here, so this is a minus term, right? Sorry, 2 into minus, right? This is 10 to power minus 3, right? Once you add this section, delta R is having a negative sign, right? But delta L's term is not having a negative sign, right? So both are having the main or numerical value same. So this will be equal to 0. This is how you explain it using mathematics. I hope you understood. right? Delta L by L is 2 into 10 to power minus 3, right? Did I write minus initially? So I'm sorry if I write minus here. It is 10 to power minus 3, right? And delta R by R is 2 into minus 10 raised to minus 3. So these two guys cancel each other. Yeah, this is a question, good question, right? Now, let's move on to the next one. I thought I rubbed it off. Elastic modulus Y, volume V, and stress elastic potential energies equation has been asked. Something you have learned during the derivation, right? So what is potential energy per unit volume? It is half into stress into strain. I've taken it, or half S strain. I can write it as stress by Young's modulus, right? So I can write it as half into stress squared into, or 1 into 1 by Y, or I can write stress squared by Young's modulus. Potential energy then will be half into stress squared into 1 by Y into volume. There are many ways you can write, right? So here has only one form, so option B. Clear? Now next question is what? A wire of Young's modulus given length 0.2 meter and cross section area 1 centimeter square is subjected to a force of 49 Newton along its length. The increase in its potential energy. So this is the last question I'm going to do from this section, guys. Right, then we'll try to move to the next chapter if possible. Let me see if the time is allowed or not. Okay, so moving on to the numerical section. Original length is given as 0.2 meter, right? Area is given as 10 to power minus 4 meters squared, right? Increase in energy means work done in compressing, right? That is L, let us say the length has decreased, right? So force I can write is half into, or I can say, let us talk about change in length. Change in length is equal to force per unit area and original length by Young's modulus, right? So I can write work or the potential energy is equal to half into stress into strain. So half into stress into strain, right? So what and all has been given? You have given force, right? So force can be used for by calculating stress by area, right? So force per unit area. So 49 is how much? 49 Newton has been given, na? Stress, sorry, yes, subjected by force. So this can be written here half into force per unit area. I'm going to write it as that is 49 divided by area is 10 to power minus 4, right? And what is strain, guys? That is change in length by original length, right? So change in length divided by original length is how much? 0.2 meter. 0.2 meter. The problem is I don't know the change in length, right? So how can I approach the change in length? So that can be written by using this one, right? So right here again force per unit area is 49 by 10 to power minus 4 into length. Original length is 0.2 meter and Young's modulus is given as how much is Young's modulus given? Nothing about Young's modulus. No, 1 into 10 to power 11 is given. 1 into 10 to power 11. Substitute this value over here. So there will be 249 and this denominator also square section, right? So you can calculate by yourself, right? You will get the answer as 2.4 into 10 to power minus 5 joules. Clear, right? So now I want to move on to the next chapter. So only few minutes we will talk about it. So mechanical properties of fluids, or this is actually from a branch which is called hydrostatics. Hydrostatics, right? So here first we'll talk a little bit about what do you mean by fluids, right? Fluids are those substances which can flow, right, and can take the shape of their container, right. And you will say that both liquids and gases both are actually categorized as fluids itself, right, but their mechanical properties are different. What you say is a liquid is something which is incompressible, that is compared to a gas, that when pressure is applied, it is very difficult to change, or it is impossible, I can say, to change the volume of a liquid, right. So for someone ask you what do you mean by an ideal fluid, means it is that fluid which is having a negligible viscosity and a negligible compressibility. Compressibility means, I hope you understood, which cannot change its volume, right, that is incompressible liquid. And what do you mean by viscosity? Something which we'll later on learn in this chapter, so I don't want to bring that in here, because I just wanted to say what is the proper definition of a fluid, right. An ideal fluid is something which is incompressible and it is having viscosity is negligible, right. Viscosity, again I'm telling you, it is something which I will later on take it. Okay, now the next term which you have learned in your throughout your life is density. What do you mean by density of fluids, right? Rho, right, that is if you asked this a small amount of, suppose if you say definition, it is actually, it is limit delta v tends to 0 delta m by delta v, then that is mass per unit volume, because density is something which you term or you find not for the entire thing. When you learn about density, suppose someone asks you what is the density of ice, you will not take the entire cube of ice, right, you will say a small volume of ice will be taken, right. So how much mass is there in that corresponding small volume, that is called density, and that volume is so small that I will say its volume is approaching 0. That's why you usually write density is limit delta v tends to 0 delta m by delta v, or I can say it is dm by dv, small mass in small volume, right, small amount of mass in small amount of volume, right. And what is the dimensional formula of density? It is mass by volume, means it is ml raised to -3, right. And what is SI unit? Kilogram per meter cube, right. And it is a property of material, right. This independent, actually someone asks you what and all it is depending upon, means density is only depending upon the material, right. It is not depending, suppose you are having 1 kilogram of ice and you have having 2 kilogram of ice, what respective of how much mass of the ice you have taken, its density is same, clear. And how much of volume you have taken, that also is irrespective, right. Density depends upon that material of constitution, right, clear. So in order to have a practical measure of density, we use a unit of volume of the material, right, clear. So that's why usually when you compare two objects with respect to density, a new term which you have to know is a new term which you have learned in your lower classes, that is relative density, right, or specific gravity. Relative density or specific gravity. What do you mean by relative density or specific gravity? It is the density of a body, right, when you are comparing with density of water, right, ratio of density of a body when compared to the density of water, that is known as relative density, right. Suppose this and all are not explicitly given in your textbook, which is something which I am giving from my side, right. Suppose it is a binary mixture. Binary mixture means there are two liquids present in this mixture, that is two fluids are there. Let's say one fluid is having mass m1 and the other fluid is having mass m2, and rho 1 is the density of first fluid and rho 2 is the density of second fluid, and they are mixed in a container. Right, so you are asked what is the density of this mixture which is having two fluids. Then how would you write? It is density is equal to mass by volume. Right, here mass I am taking means it will be m1 plus m2. Right, total mass of both of these guys. Then and volume will be what? It will be what? Mass m1 by rho 1, that is the volume of this guy, plus m2 by rho 2. Right, that's how you write it. Right, so here m1 m2 section, suppose that is the rho, that is density of a binary mixture is equal to m1 plus m2 divided by m1 by rho 1 plus m2 by rho 2. Right, now what happens if the liquid you have taken, both the section binary mixtures are having equal masses? Thus m1 is equal to m2 is equal to m. So I can write rho is equal to the section all cancels out, 2 rho 1 rho 2 divided by rho 1 plus rho 2. So a binary mixture's density which is having equal masses of liquids is equal to this much. Right, similarly if you have taken equal volumes, that is v1 is equal to v2 is equal to v, then density is equal to rho 1 plus rho 2 divided by 2. This is arithmetic mean. This is also called harmonic mean. Harmonic mean, this is arithmetic mean. Clear? Right.